In this section 10.3, we're just going to explore some more identities that are often used in trig. So like 10.2, we'll look at the identities, we'll do some computations, and then we'll do some verifications or some proofs of identities. What we're going to focus on in this section is the double and the half numbered identities. I will typically call these double number, which is what we're going to look at first, double angle identities, because that's just what I'm used to. So double number, double angle means the same thing. And when we look at the first three, they're all cosine of 2 times an angle, which is why it's called a double angle. We actually proved or verified these first two in example 3 from our last section, 10.2. We verified cosine of 2a equal to 1 minus 2 sine squared a, and in the process of that verification, we actually did the cosine squared minus sine squared. So the third one, cosine of 2a equal to 2 cosine squared a minus 1, to verify that, it would be the same process we did in 10.2 example 3. So what I'd like to start out with, instead of a computation, is verifying that sine of 2a is equal to 2 sine a cosine a, and that will be our example 1. Also note the tangent, and typically the tangent formulas tend to be a little bit more challenging to work with because tangent is a fraction. It's sine over cosine. So oftentimes in tangents identities, you will see a fraction. And in this case, it's 2 tangent of a over 1 minus tangent squared of a. But again, let's go first to example 1. We're going to verify this identity that sine of 2a is equal to 2 sine a cosine a. This particular identity is used extensively in calculus. I'm going to start on the left-hand side, sine of 2a, because I know I can break this up as sine of a plus a, and then I can simply use my addition formula for sine that I had from our last section to write this as sine. Oops, don't know why I started to write cosine. That's just me. Sine of a, cosine of a, plus cosine of a, sine of a. Sine a, cosine a, and cosine a, sine a, those are the exact same terms because it's multiplication and that's commutative. So these are actually two of the same thing, and I could simply write 2 sine a, cosine a, and I'm actually done. Now let's go ahead and use this. So let's say, again, I don't have a calculator and I want to figure out what 1 minus 2 sine squared of 22.5 degrees is. Well, I don't know what sine of 22.5 degrees is without a calculator, but notice that this looks like cosine of 2a. It's 1 minus 2 sine squared of an angle, and in this case, our a is going to be 22.5 degrees. So I can write this as cosine of 2 times 22.5 degrees, which is equal to cosine of 45 degrees. And now I know what the answer is. It's square root 2 over 2. So the purpose of using these identities is, once upon a time, calculators were not very common, or computer software was non-existent. So we had to use different identities to figure out angles that we actually don't know from our unit circle. In example 3, this looks like the tangent of 2a formula, but notice here that we have a 4, not a 2. However, 4 is 2 times 2, and I can easily break this up into 2 times the tangent of pi over 8 over 1 minus tangent squared of pi over 8. So you may not see the formula written exactly as it's given, but if you can manipulate in some way so that you can use the formula, that would be nice. So notice that this is actually 2 times tangent of 2a. And in this case, our a is equal to pi over 8. So this is 2 times tangent of 2 times pi over 8. And 2 times pi over 8 is simply pi over 4. Now tangent of pi over 4 is 1, so this just becomes 2 times 1, which is 2. In example 4, we're going to find sine of 2a, cosine of 2a, and tangent of 2a, given that cosine is a positive 4/5 and sine is negative. So with respect to angle A, if cosine is positive and sine is negative, then A is in quadrant 4. Now, I don't know if I'm going to need that or not, but it's good to know that A is in quadrant 4. Now, that doesn't tell us what quadrant 2A is in. Let's go ahead and find sine of 2a. Now there's only one formula. That would be 2 sine a cosine a. And now I know what cosine of a is. That's given to me. That would be 4/5. So when I multiply the 2 times the 4/5, I get 8 over 5 times sine a. But I don't have sine a. One thing I could do is I could use the sine squared plus cosine squared is equal to 1. And I could solve, because I have the cosine squared, I could solve for the sine. And that's fine. And we've been using that quite a bit over and over and over again. But what I'd like to do is just remind you of the properties with right triangles. So if I were to drop a right triangle, because I know that with respect to angle A, cosine is adjacent over hypotenuse, and adjacent would be 4, hypotenuse would be 5. So I know that cosine of A is 4/5. If I use my Pythagorean formula, I can find that missing side as 3, right? Because 5 squared is going to be equal to 4 squared plus, it would be 3 squared. And now I know that sine of A, now remember, sine of A is negative, so I know it's going to be negative. So we can use this right triangle, but we have to still determine, based on quadrant, if the value is going to be negative or positive. So I know that sine of A is going to be opposite over hypotenuse. So that would be a negative 3/5. And I also get tangent as well, just in case I need it, which would be, we're in quadrant 4, so tangent of A is going to be negative as well, and it's going to be opposite over adjacent, so negative 3/4, just in case I need it. I know sine of A is negative 3/4, so now I can do that multiplication to get negative 24 over 25. I'm going to rewrite this to remind myself that this is my sine of A, which is negative 24 over 25. Now again, using the identity would work perfectly fine. I just wanted to bring back that idea of right triangles because they're so powerful. Let's go ahead and find cosine of 2a. I have 3 formulas to choose from. I'm going to use the first one. And the only reason why I'm going to use the first one is because sine of A is negative 3 over 5, and cosine of A is positive 4 over 5. They have the same denominator. When I square them, I'm just subtracting fractions that already have the same denominator. If I were to use the other 2 formulas for cosine, that would be the 2 cosine squared minus 1 or the 1 minus 2 sine squared. I would have to multiply, or I'd have to square, multiply by 2, and then I have this subtraction where I have to replace the 1 with a fraction, common denominator, and then do the subtraction. So I think it would be shorter But it really doesn't matter which one you choose. All three are equally fine. I think it'd be shorter for me to do cosine squared minus sine squared. Remember cosine, that was 4/5. Square it minus sine, negative 3/5. Square it, we get 16 over 25 minus 9 over 25. Oh, my handwriting is getting really bad. Which would give me a 7 over 25. And remember, that was our cosine of 2a. The last thing we need to find is tangent of 2a. Tangent of 2a, well, the formula is hideous. I do have tangent of a, so I could easily use the formula. So remember, the formula is tangent of a, well, sorry, 2 times tangent of a. So I'd have to do 2 times negative 3 over 4 over 1 minus negative 3 over 4 squared 1 minus tangent squared. And I don't feel like working with that. So maybe I could just use the fact that tangent is equal to sine over cosine. So tangent of 2a is equal to sine of 2a over cosine of 2a. And I already have sine of 2a and I already have cosine of 2a. So I think that would be much easier to use. This is going to be equal to sine of 2a was negative 24 over 25. Cosine of 2a was 7 over 25. So recall that common denominators we can cancel. And I get the tangent of 2a, and I'm going to just rewrite this, is equal to negative 24 over 7. Okay, so let's go down to the very bottom here. We're going to introduce some half number or half angle identities. So in this section, we're looking at doubling our angles and halving them. So our half number or half angle, which is what I'm usually going to be calling it, is simply taking your angle and dividing it by 2. So cosine of our angle over 2 is equal to this hot mess. Look at the sine of a over 2. And then tangent actually has 3 different forms. They're all pretty bad. Whenever you're halving something, you're creating a fraction, which is why all of these 5 formulas have nasty looking fractions, and most of them have square roots where you have a plus and minus. You have to choose whether you're going positive or negative based on the quadrant that a over 2 is in. So we'll use these in just a second, but there's a little note that I have down here. Is in this section in your textbooks, there are some lesser used identities that we'll not cover. These identities, quite frankly, are very, very rarely used. And as a student, I actually never use these in my calculus courses, and that would be product to sum and sum to product. So you could go ahead and go over those identities if you wish in the book, but you're not responsible for using those particular identities. Now let's use our half angle formula or half number identity to evaluate. Here we have cosine of pi over 8. Now I don't know what cosine of pi over 8 is unless I use a calculator. Again, the point is to not use a calculator. So in this case, pi over 8 is in quadrant 1. So I know cosine is going to be positive, which means when I choose which formula I'm going to use for cosine of pi over 8, I'm going to choose the positive square root. So that's important. Another thing that I need is I need cosine of a, not cosine of a over 2. So cosine of pi over 8, if I'm using the half-numbered formula, which is what I'm supposed to use, that tells me that my a over 2 is the pi over 8, which means a, if I multiply both sides by 2, I get 2 pi over 8, which is simply pi over 4. So at least I know what cosine of a is. It's going to be cosine of pi over 4. Now when I use my formula, I'm going to choose the positive square root. It's going to be 1 plus cosine of my a value is pi over 4 over 2. And now remember, this whole thing is underneath a square root. Cosine of pi over 4 is square root 2 over 2. And this becomes 1 plus root 2 over 2 all over 2. Everything's underneath this square root. And I'm done. I figured out what cosine of pi over 8 is, except for this is not simplified. This is a complex fraction. So underneath this square root, what I'm going to do is I'm going to multiply the top and the bottom by the denominator of 2. So you could write 2 over 1 or just 2. When I do that, I'm going to get, so here the 2 times the 1 would give me the 2, plus when I multiply the 2 times the square root 2 over 2, the 2's cancel. So this becomes plus square root of 2. And then in the denominator, 2 times 2 is 4. So recall that this is all under the square root. So now if I separate the numerator, which is square root 2 plus square root of 2 over denominator would be square root of 4, I can see that the denominator is going to be 2. I get the square root of 2 plus the square root of 2 all over 2. And although this still doesn't look that much better, it's actually written in the simplest form. There's nothing else I can do to simplify. The most I could do at this point is approximate this value by using a calculator. Oftentimes using the half number or half angle formula will give you values such as this, because when you look at the formulas, a lot of them are square roots where you're putting fractions underneath square roots. Okay, so in example 6, we want to use the half number identity to find an expression for the exact value for this function. So it says tangent of x over 2 given that, or given, sorry. So that means this is what we need to find. We need to find tangent of x over 2. We're given the information that tangent of x is negative square root 5 over 2, and x is between pi over 2 and pi. So I know that x is in quadrant 2, but I don't know what x over 2 is. And I need to know that because I'm trying to find tangent of x over 2. I need to know if it's going to be a negative or a positive value. So I can easily figure out what that is. Notice with this inequality, if I simply take each of these values, which I'm allowed to do in an inequality, and divide by 2, I now have x over 2. It's going to be less than pi over 2. And then simplifying the pi over 2 over 2, that's going to be pi over 4. So I have that my x over 2 is between pi over 4 and pi over 2, which means this is in quadrant 1. So at least I know that tangent of x over 2 is positive. So I might need to know that if I have to choose between a negative and a positive value. To use the half angle formula for tangent of x over 2, I'm going to need to know either cosine or sine and cosine, depending which formula I choose to use. Now, it appears that the last two formulas would be the easiest to use because there's no square root in them, and I don't have to choose between the plus or a minus. But for all of them, I'm going to need at least cosine of A. And for the last two, I need both cosine of A and sine of A. So I could, again, use identities to figure out what these are. I have tangent, but something I want to caution you against. We know that tangent of x is equal to sine of x over cosine of x. And since tangent of x is negative square root 5 over 2, some may want to say, oh, okay, well, the sine of x is going to be that square root of 5. Cosine is going to be 2. Don't know where the negative goes. You can't do that. Remember, cosine and sine, the values have to be between negative 1 and 1. Cosine of x can't be 2. Sine of x can't be square root of 5. Those are both greater than 1. Think about it this way. If I told you that 1 half is equal to 2 fourths, which is true, that does not mean that 1 is equal to 2 and 2 is equal to 4. So this is not a property that we can use. Again, I'm going to have to use identities, or what I could do is drop a right triangle. I have tangent of x. I can easily find cosine of x and sine of x because I know that x is in quadrant 2, so sine will be positive, cosine will be negative, and tangent of x is, ignoring the negative, opposite over adjacent. So I'm going to go ahead and do that. I'm going to drop a right triangle with respect to my angle x. Ignore the negative. Tangent would be opposite, which is square root of 5, over adjacent, which is 2. I just need the hypotenuse. 5 square root of 5 squared is 5, plus 2 squared is 4. So that will give me 5 plus 4. It's going to give me 9. Square root of 9 is going to be 3. So I know that my hypotenuse is 3. So my cosine of x in quadrant 2 would be a negative 2/3, and my sine of x in quadrant 2 is a positive square root of 5 over 3. So I have both cosine and sine. I can use any one of those three formulas. I'm going to use the second one. I don't feel like using that one with the square root, the first one. So I'm going to use the tangent of a over 2, and in this case our a is x, so tangent of x over 2 is equal to sine of x, which is square root of 5 over 3, over 1 plus a negative 2/3 would be a minus 2/3. So that does look kind of icky. But in the denominator, 3 over 3 minus 2 over 3 is simply 1/3. And what's nice about this is I've created a complex fraction where denominators are the same, so I could simply cancel those. And the square root of 5 over 1 is the square root of 5. I did have an error in here. I don't know if you noticed this. Oh wait, no, I don't have an error in this. This is actually correct. So x over 2 means that the tangent value will be positive. So, I'm right. Tangent of x over 2 is square root of 5. Thought I had an error, but I don't. Now, let's use the first one just for fun. Remember, we were choosing the positive square root. And the nice thing about this one is that it only involves cosine. So in this case, cosine is negative 2/3. So the numerator, where it's 1 minus cosine, will be 1 minus a negative. It will turn into 1 plus 2/3. And then in the denominator, we have 1 plus a negative, so it's 1 minus 2/3. So 3 over 3 plus 2 over 3 will give me 5 over 3. and then 1 over 3 in the denominator, so you could see that the 3's would cancel, and this would be the square root of 5 over 1, which is simply the square root of 5. So that wasn't bad either. Actually, the worst one would be the last one. That would take a little bit longer because sine of x is in the denominator. Sine had the square root of 5. So I'll show you what I mean. Even though I've already done 2 of them, I know square root of 5 has to be the solution. But if we did use 1 minus cosine, so that would end up being a plus. Cosine of x was the 2/3. And then in the bottom, I would have the square root of 5 over 3. So you see, I'm going to have a square root of 5 in the denominator, which is fine, but that just means that I have to do some rationalizing. So in the numerator, I get 5 over 3. Denominator square root 5 over 3. We could see that the 3's will cancel. That would be 5 over the square root of 5, and I have to rationalize. So the first 2 formulas were actually the best because I didn't have to worry about rationalizing denominator. And then this is going to be 5 square root 5 over 5, and cancel the 5's. Still works. Just a added step of rationalizing and then simplifying. The last thing we're going to do in this section is we're going to do a verification. Now, I would not test you on verifying a half angle because you see that the half angle identities or formulas are all fractions. They are fairly complicated. So the verification, they're usually fairly long. Let's see, but we'll do one. And you may have one on homework, but not tested on this. It's just too long. It's not worth the time. So example 7, we have cotangent squared of x over 2. So the x over 2 tells me half angle or half number identity. And I could start with a cosine squared, which is what I'm going to start with. So remember, when we verify, we always have to state what side we're starting with, and we have to work our way to the other side. So I have 2 choices right now. I can do the reciprocal 1 over tangent squared, and I know the formula, half angle formula for tangent squared. I'm going to have to choose between 3 of them. Or I could use cotangent is cosine over sine. And now when you look at the right-hand side, you see that there's a cosine in the numerator and a sine in the denominator. So it seems reasonable to change this to cosine over sine. And then now I can replace, because I need cosine of x, not cosine of x over 2. Now I can replace the numerator and denominator with the formulas that we have for half angle or half number, cosine and sine. Cosine, oh, well, you know what, let me rewrite this just to remind you that this is cosine of x over 2 quantity squared. That might make it easier to see how we replace with the formula. And the denominator is sine of x over 2 quantity squared. So when I replace cosine of x over 2, that's going to be plus or minus the square root, you know what? I don't know if I'm going to have enough room. That's going to be plus minus the square root, I'll put the square root in later, 1 plus cosine of x over 2 square root plus minus sine of x over 2, 1 minus cosine of x over 2 square root with a plus minus. So remember, we're squaring all of this. So far things should make sense. They just look bad. Now, when we distribute this square on the outside, it's going to square the plus and minus. So if you square a positive, it's a positive. If you square a negative, it's a negative. So the plus minuses will be gone. And when you square a square root, they cancel out, which means this is actually going to be really nice. The plus minus and the square roots are gone. I end up with, I forgot my equal sign, I end up with 1 plus cosine of x over 2 all over 1 minus cosine of x over 2. And I don't know if you can see that we have this common denominator that cancels. I have 1 plus cosine of x over 1 minus cosine of x. And I'm kind of stuck. This is close to what I want. Let's go back and look at where we need to end up at. We need a 1 plus cosine of x squared. So 1 plus cosine x times 1 plus cosine of x. And in the denominator, I need a sine squared, but I'm going to ignore that for now because my numerator almost looks like 1 plus cosine of x. I just need one more, 1 plus cosine. So this is a fraction. I'm going to simply multiply top and bottom by 1 plus cosine, so at least I can get my numerator to match. So again, working from the left to the right, the goal is to get the right side to match what's in the identity. 1 plus cosine of x squared is now done. But now in the denominator, if you multiply out the 1 minus cosine, 1 plus cosine, so remember these are conjugates, the quick answer is 1 squared minus cosine squared. So it's the first squared minus the last squared. Or you can multiply it out and see that you'll get a plus and a minus cosine that will cancel. Regardless, we get 1 minus sine squared. And then 1 minus sine squared, going back to the Pythagorean identities, is cosine, or 1 minus cosine squared. Sorry, I'm skipping steps. 1 minus cosine squared. Okay, that makes more sense because 1 minus cosine squared is sine squared. This becomes 1 plus cosine of x squared over sine squared. Whew. Very long. We didn't have to do it that way. There's other ways as well. If we did start at the left-hand side, which is our cotangent squared, we could have gone 1 over tangent squared of x over 2. Now the advantage is that if you look at what we need to end up with, and you compare that to those half angle formulas, you'll see that that looks very similar to the middle one. Tangent of x over 2 is equal to sine of x over 1 plus cosine of x. So the only difference is that it's not squared. So I could have replaced the tangent squared of x with sine of a 1 plus cosine of a. Let's see what that would look like. Or sine of x, sorry. And now remember that's squared. And then this is now almost what I want. Let's distribute the square top and bottom. So it's going to be 1 over sine squared, 1 plus cosine of x squared. And then properties of fraction, 1 over the sine squared, 1 plus cosine squared. You would flip it and you would get 1 plus cosine of x squared over sine squared x. So that one we're done. It took less steps. It didn't seem like it would be shorter. So oftentimes when you do verifications, your first instinct may be to switch everything to sine and cosines, and that's absolutely fine. And you should get to where you're going, but it just may take a little bit longer. It was actually shorter if I use the reciprocal that cotangent is equal to 1 over tangent. So that's it for this section.